Final speaker for the day is Silvain Rideau, speaking on imaginaries and pseudo-p-adically closed fields.
Hopefully this is working. And it's not making too much weird noises. Yes, so this is joint work with Samaria Montenegro, and this all essentially started because, well, her PhD thesis is mainly about pseudo-p-adically closed fields and pseudo-real fields, and there are two obvious dissymmetries. Everything is proof of both except for two results. One of them is elimination of imaginaries. So this is well, solving that problem. So we have, well, we haven't seen pseudo-p-adically closed fields yet, but we have seen fields that are very similar to those which are pseudo-real closed fields. And so a pseudo-p-adically closed field is essentially the same thing where you replace the order by a p-adic valuation. So let me define it. So a valuation is said to be p-adic if the residue field is Fp and P has minimal positive valuation, which exactly means that you can be embedded in an elementary extension of Q. And field extension is totally p-adic if every p-adic valuation extends to a p-adic valuation of L. And it is said to be pseudo-p-adically closed if it's existentially closed as a ring in every regular totally p-adic extension. As often in model theory, we are not interested in pseudo-p-adically closed fields, we are interested in those that are tame enough, and so in our particular case, we're going to look at the bounded ones, so that those that have finitely many extensions of any given degree. By a result of Sami, those fields are NTP2, although it's not going to play a role in that talk.
Sorry, what fields are NTP2?
Bounded pseudo-p-adically closed. So yes, obviously there is a question of in which language should we consider them. A priori we want to look at them in, well, either we look at them in the ring language or we add the valuations around. And so a result of Sami is that actually this does not matter. Because if you have a bounded pseudo-p-adically closed field, there are finitely many p-adic valuations and they're all definable in the ring language. So any treatment of pseudo-p-adically closed field, bounded pseudo-p-adically closed field, will have to deal with the valuation.
And you need constants for defining.
Yes. Definable here means definable with constants. Yes, so now if we want to study imaginaries in a bounded p-adically closed field, we'll have to deal with the imaginaries that arise from valuations. The good thing is that we actually know in general what these imaginaries are, and so they are usually called the geometric imaginaries. So if KV is a valued field, then we define the geometric sorts Sn and Tn in the following way. So they are both quotients of GL and K. And so O here is the valuation ring, and I'm not going to exactly, well, to define what this group is, because it's not relevant to this talk, because we'll be mainly looking at well, except for a theorem down this page, we'll be looking exclusively at fields with discrete valuations, and then if you have a discrete valuation, then Tn can be easily embedded zero definably into Sn+1. So you don't really need to care about Tn. So the language we're going to look at is the geometric language, which has infinitely many sorts. It has a sort for the field. It has and then infinitely many sorts for the Sn and Tn. And it also, well, it contains the ring language on F and the canonical projections from GL and F to Sn and Tn. One might wonder, where is the valuation gone? And well, it is here, because S1 is exactly the value group, and little s1 is the valuation. Actually, you also have the residue field around, and you have, well, as the next important theorem tells us, you essentially have everything you need. The reason this language is used is the following result of Rushavsky, Haskell, and McPherson, that algebraically closed valued fields eliminates imaginaries in this language. Well, this result has since then been extended to many classes of valid fields, and I think one relevant other example for this talk is that if you take an actual p-adically closed field, not a pseudo-p-adically closed field, then it eliminates imaginaries. It also eliminates imaginaries in LG, so this is a result of Krzyzewski, Martin, and myself. Alright, so now let's see where we're at. We have our field, we know we have n valuations on it, and we know that each of those valuations give us geometric sorts. So naturally, if we want to eliminate imaginaries, we'll have to add all these geometric sorts. The reasonable question now becomes, is that enough? And the reasonable answer is hopefully.
Now when you say all these geometric sorts, it just means separately for each valuation?
Yes. So you add you obviously need to, well, okay, maybe not. Maybe there is some coding that happens that makes things magically happen, but at first sight, you really need to add all the geometric sorts for the separate valuations. Well, to add them separately, and what you hope is that this is enough. And so a first result towards proving that this is enough is that the valuations really don't interact at all. So let me fix a few notations. So K will be a bounded pseudo-p-adically closed field with n p-adic valuation that I will denote Vi. And let Li denote n copies of LG, which will correspond to each of the valuations. And so their sorts I will call Gi for the ith geometric sorts, and they all share the sort F. And so what I do then is look at I will work in the following language. So I add the geometric sorts for each valuation, and then I also add constants for an elementary substructure because, well, you kind of need it. Well, you need it. And so the theory we'll be interested in this talk is so the theory of K in this language. And so let me fix some more notation. So so I will be working in the model M of T, and I will denote by Mi bar a model of ACVF, which is the algebraic closure of M with an extension of Vi, and Mi will be the p-adic closure of M inside Mi bar. Okay. So the first...
Is that the same as Hanselization with respect to Vi? What is
yes, it is. It is the Hanselization because,
okay.
well, because the value group is Z group. The value group for each valuation of the pseudo-p-adically closed field is Z group. Yes. So,
sorry, is that part of the definition of p-adic?
No, it just happens to be the case. Yes, so the first clue we have that the valuations don't interact at all is the following, is that the valuations are what's called independent as valuations. And so, which can be translated in the following way. Whenever you take a collection of open for the various valuations, well, non-empty open, and you intersect them, you get something non-empty. But, I mean, this is very nice, but this doesn't tell us anything about definable sets. So we want a statement that that is actually about definable sets, and so we prove the following statement, which is really an orthogonality, a bona fide orthogonality statement, which tells us that whenever we pick a tuple of geometric sorts where each coordinate corresponds to one valuation, then the complete type of that tuple is completely determined by the type of each coordinate in each p-adic closure. So this appears to be a unary statement, but it's not at all, because if you have a collection of geometric sorts for a single valuation, then it easily embeds into a larger geometric sort. So this is really an actual orthogonality result. It's actually more than an orthogonality result because it also tells you that the geometric sorts are pure. As well, the only structure you have on it is the structure given by the p-adic closure. So now, once you have that, it's not very hard to see that if you look at the definable set, so you have weak elimination of imaginaries for sets defined in the geometric in the geometric sort just from the fact that the p-adic closure eliminates imaginary. But this is far from being what we want, because this is only talking about the geometric sorts, and we're kind of missing the most important point, which is the field. So we need something much better than that to get going. And so what we would like to do is describe definable sets in a canonical way, obviously, if we want to eliminate imaginaries. And so in her PhD, what Sammy did was prove a density result of which you saw a form yesterday for PRC fields. So she proved that every definable set is dense in the union of multicells. But the problem is that the multicells are not canonical. So you can't use that to eliminate imaginaries, and actually proving that the multicells are canonical seems to be very hard. Well, at least we don't know how to do it. So what we decided to do is, instead of trying to describe definable sets, we're going to do something simpler, and we're going, well, yes, we're going to describe groups. So what we're going to do is take any set of imaginary elements, and which is algebraically closed. So we only need a weaker version of being algebraically closed. We just need to know it's algebraically closed in the geometric sense. And what we want to do is to describe all types over A. Once again, this is a very complicated problem because, well, because we don't really have a quantifier elimination result for PPC fields, so we need to do something a bit quicker. So what we're going to do is show actually that this type is consistent with certain invariant types. So this is the result we prove. So this is the one-dimensional result. So we take an element in the field, and then we can find types pi in each algebraic closure that are invariant over the relevant geometric points, and such that this whole thing is consistent. So I say that this is a local version of Sammy's result because it's really, if you look at it, it really is telling you that every type lives on the outer edge of some intersection of balls for its valuations. And actually, you can describe very precisely what the PIs are. It's very easy. It's just the intersection of all balls for the valuation VI that, well, it's the generate type of the intersection of all balls for the valuation VI that are A-definable. Yes.
What is MI bar again?
It's the algebraic closure with an extension of the ith valuation. And without the bar, it's the p-adic closure. Yes. What?
Okay.
And the proof of that result actually uses orthogonality to show that there cannot be any interaction between the balls to prevent this type from being satisfied. But what you really want to prove elimination of imaginaries is something in higher dimension, because as we know, unary elimination of imaginaries is not very, does not imply full elimination of imaginaries. So you need an NRE version of that. And so what we decided to do, despite this seeming very silly because of what I just said, we decided to just prove it by induction. But there is a problem, which is that here we're working over an algebraically closed set, and here we just have one point. We added a new point, and so we need to close to go to the algebraic closure. And so this is what this does. So whenever you have a tuple of field elements and something that lives in the algebraic closure over A of this tuple, if the MI bar type is GIA invariant, so is the MI bar type of it. So this might seem like a very, this might seem like it's an easy consequence of, no, it does not, but if M is an IP and we know elimination of imaginaries, this is an easy consequence of work by Ann and but we don't know elimination of imaginaries. That's exactly what we're trying to prove, because we really want something GIA invariant. And also, the type here is actually, it's a weird type, because it's a type in the algebraic closure. So it's not a complete type anyway. So we have to work more. And actually, the proof of this proposition is exactly where functions get coded. Functions definable in M get coded here. Well, actually, their germ get coded, but this is enough to get us going. So now once you have those two things, it's very easy to prove that this holds in higher dimension.
C is in mi bar. Mi bar contains M.
Yes?
Mi bar contains M.
Yes.
But then
It's the X algebraic closure.
But then C is in M. In mi bar.
C is in M.
So C is in mi bar.
No, well, it's also in mi bar, yes.
So the type of C over mi bar.
Ah, okay, yes, sorry.
Sorry.
C is in an elementary extension, I'm sorry.
What?
Yes, I was sloppy, you're right. I was very sloppy. This is also C, yes, so yes, sorry, I take C in an elementary extension of M, of course.
So really, you're working actually with a...
With a type. I'm working with an invariant type, and I'm saying that the algebraic closure for M of that type is also invariant. Yeah, this is what I mean. I'm sorry, the C lives in an elementary extension. Oh, otherwise, this is, you're right, this is a very silly, silly proposition. Yes, but once you have those two with the actual better version, with the actual non-trivial version, it's very easy to prove the higher dimension version. Okay, so actually you can even work a little more and to do something, and nobody noticed, but between the two slides the bar disappeared. So you can actually, because so far we only had algebraic, so we only had types in the algebraic closure, and if you work a little more, you can actually make it a type inside the p-adic closure. So it also tells you about being an nth power in the p-adic closure. Okay, so once we have that, we have the impression we have done serious work, and in fact, if M were a p-adically closed field, and so we'd have only one valuation, the type pi would be a complete type, and so we would have proved we would have proved something which is enough to get elimination of the weak elimination of imagery. Actually, if you look carefully, we haven't used here we used elimination of imaginaries in ACPF, but we haven't used elimination of imaginaries in QP, and so actually once you get there, you get another proof of elimination of imaginaries in QP, which is, well, not that different from the other proof, but which has a few differences. Yes, so now how do we get from there to elimination of imaginaries? Well, we need a result that tells us that these types essentially already encode a lot of information. So we know that they're not complete types, so we need something else. And so what the something else will be is an amalgamation result. Okay, so let me once again set up a few notations. So I'm just going to give a completely abstract statement which will apply in our case. So I'm going to take a collection of languages sharing a dominant set so D, and I take a language that contains all of that, and I take theories TI, which are Li theories, and a theory that contains the universal part of all of the TIs. So in particular, whenever I take a model M, I can embed it in a model Mi of Ti, and I take all of these to be sufficiently saturated and homogeneous. Actually, I want the Mi to be homogeneous over M, not just over smaller parameters. But and then I need the notation. So I will write that A is independent from C over B if I can find invariant types for each of the valuations. Well, no, it's not valuation. Sorry. Now it's just languages. So if I can find invariant types for each of the LIs, such that A realizes the union of the invariant types over the relevant parameters. And so with all of that, I can now write a criterion for weak elimination of imaginaries, which goes as follows. So first, I assume that whenever I have an algebraically closed set of imaginary points and a tuple, a dominant tuple, then I can actually assume that up to taking an equivalent point, I can actually assume that it's independent from M over A. And actually, this is what we have proved so far. This is exactly what we have proved so far. And this is the second ingredient I was talking about, which is the amalgamation result. So maybe a drawing would be much clearer. So what we're doing is the following. We have a base A. Should I Could I do it bigger, maybe?
Well, so
Come to this
Oh
one.
yes, I should move it in the left. And then we have, yeah, let me do it much bigger. I mean, I just need to draw that. So.
in fact, you could put it right in the middle so that
Oh, the light will be on it.
I know.
Oh, then, no, that's a bad idea.
sorry.
So I have a base A, and I have 3 points. A, B, and C. And I assume that those two are equivalent in M over A. And I assume that, well, I assume various independence, so I assume that this one is independent from this one, and that this one is independent from those two. And I assume that the type here, so the type of this pair, is the same as the type of this pair, but just, so quantifier free. Well, that's not really it, but for every Li. And then the conclusion tells us that I can find another point D, such that actually the type of the pair is the same, and that's, moreover, I've kept one of the two types. Okay, this is exactly what it says. So if you have 1 and 2, T weakly eliminates imaginary. Okay. So I want to point out that even if you take L, if you take only one Li, and you take L to be equal to Li, something is still happening. 2 is completely trivial in that case, because, well, this is the same notion as that, so nothing is happening there. But you are still saying something which is a criterion for weak elimination of imaginaries, which is relatively well known, I think, which is that if you have enough invariant extension over the right basis, then you have weak elimination of imaginaries. So, yes. In particular, this is the criterion I've used a number. So the version where Li and L are the same is the criterion I've used a number of times to prove elimination for VDF and other theories like that. CDF and
So,
yes. Someone had a question.
yeah, and I couldn't completely read it, but where's the place where you separate, where you say something separately for each Li? I only see places where it's all of them together. So what's the difference?
Oh, I don't say anything for each Li.
So what's the difference between that and just putting L, you know, taking the union of these languages?
Because the PI
Oh,
live in MI.
oh, I see. So there, well, yeah, thanks.
I mean, you can probably phrase it in terms of quantifier free type. I mean, you can phrase it in terms of quantifier free type, but I did not do it here. Actually, if you look at this, this also is a way of so not formulated exactly this way. Well, actually, no. So formulated exactly this way, it can be used to prove that PAC fields also eliminate imaginaries, and with a slight change, reformulating it in terms of quantifier free type, you can also use it to prove that ACFA eliminates imaginaries.
But do you have somewhere this orthogonality principle of the various LIs that you mentioned earlier?
No, actually that's what I said at some point, which is that the orthogonality is used to prove that.
Yeah, and is that
And so
assumed?
then it becomes hidden in there.
And then that's assumed, okay.
Yeah, well, because that's, so proposition, the corollary is
it's
exactly
assumed in the
hypothesis
abstract-
1.
In the abstract statement. Okay.
Okay, so so now, how long? Oh, I have 5 more minutes. So now what we're left with is prove amalgamation. So I'm not going to actually prove amalgamation, but I'm just going to tell you that amalgamation follows from a more complicated statement, which really looks like a kind of independence theorem where you first verify that there is no quantifier free obstruction to the independence theorem. Okay, so you take an A1, an A2, this should be CI, I'm sorry. Oh, no, this is C, sorry, this is C. A C1 and a C2, and then you have a witness that there is no quantifier free obstruction to independence, and then you conclude that there is no, that you actually have a witness of the independence theorem. And so if you know that, then you can easily prove that more That's seemingly more weirder. I think, well, this result seems a little, I think this result seems more natural, and it's actually more natural to prove. A few remarks. If you assume A to be in the field itself, and not in the geometric sorts, this is an earlier result of Montenegro. But this is not sufficient to prove elimination of imaginaries. It's sufficient to prove geometric elimination of imaginaries, but not weak elimination. So actually, you can check that if you use the older version and the description of the structure of the geometric sorts given by the orthogonality result, you can prove that. And then once you have all of that, you can actually prove our theory. So the theory T eliminates imaginaries. You might have noticed that I hid something under the rug, which is that previously I was talking about weak elimination, and suddenly now I'm talking about elimination of imaginaries. So as always, what you need to do is code finite sets. It's not as obvious as it sometimes is, because you have to deal with finite sets that live in product of geometric sorts for the various valuations. And this is not completely obvious. I mean, it's doable, but it's not completely obvious.
Right? Why don't they just split into unions of finite sets in each one?
No, you can have you can define the bijection. I mean, yeah. So what you have to prove is that if you define a bijection, then you actually know all the points.
Yeah.
Well, that's not how I prove it, but that's essentially what you prove. Or maybe it's completely obvious, but it was not completely obvious for me for a while. Because somehow orthogonality doesn't tell you anything about finite sets.
Oh, I thought it did. Okay.
Well, maybe it does, but I'm not aware of it. Also, as I pointed out earlier, since the valuations are discrete, you don't really need the TIMs. Well, you really only need the SIs. And one last point is that if you don't like having all these geometric sorts for all the valuations around, you can do something very neat, which is that you can actually pretend that you have a valuation ring around. So if you take O to be the intersection of all the OIs, so O is not a valuation ring at all, but you can look at this thing that really looks like the SN for O. And actually it does code the O lattices, and this is isomorphic to the product of the SNs, quite easily. I mean, this is just due to the independence of the valuations. And so in the end, if you want, instead of having all these geometric sorts around, you can have just one family of geometric sorts that corresponds to this ring. And this is the end of my talk.
Are there any questions? Okay, in that case, let's take a more time.